So I believe last class we touched on the detection of alpha, beta, and gamma radiation, right? I mean, these are stuff that we would have known a little bit about from fifth form days, and we're gonna go through how can we easily identify when an alpha particle is being emitted, when a beta particle, when a gamma particle is being emitted, and what are the actual nature of these particles, right? So we must know these things. And of course, as we made mention last class, these are what we call ionizing particles, right? They are called ionizing particles or ionizing radiation because what they generally do is that when they pass through other particles, such as air and so forth, they ionize them, meaning that they allow, maybe one particle to gain, to become more positive by way of knocking an electron off one of its shell and all of that, right? And I believe last class we said, hopefully we said it, that alpha particle has a high ionization property or ability. Let me see the chat here. Well, I'm speaking very loud as possible. I don't know how much louder I can go, but let me know if you guys are hearing me. I'm speaking very, very loud.
I can hear you.
Yeah, Ro, I'm not sure what's happening on your end, but actually I chat too loud in my house. You understand? But yeah. Not sure what the issue is. But what I can do is I'll try to disconnect and connect my audio again, and hopefully that will work for you. All right, just give me a second. Right. I hope it's better now. Not sure. But either way, yes. So we're talking a while ago about the whole properties of alpha particle, or what can it do, right? We said that it can cause it has high ionization properties, meaning that because of the nature of alpha, alpha is going to be a helium nucleus, so to speak, right? And you can expect that that is going to be much heavier. So when it collides with those electrons on the outer shell of an air molecule, then it's going to easily knock out an electron from the shell. So that's the reason why we said that it has high ionization abilities, right? Now, this is what happens for when alpha particle is being produced, in a sense, right? Whenever an element gives off an alpha particle, it really does that so that it can reach to a point of stability very easily. And you have some elements that will easily give off an alpha particle or will easily give off a beta particle and will also give off a gamma particle easily, right? Now, for that to happen, what you're going to realize is that the element is going to lose some of its positive charge, depending on what element it is. Whenever it loses 2 protons, then we can clearly identify that that is going to be an alpha particle. Whenever you realize that the element loses an electron, then clearly that's going to be a beta particle that is being given off, right? When it comes down to gamma now, if you don't realize that there's any change in the proton number or the mass number, then obviously that is going to be a gamma ray that is being given off, right? And as you can see here, it tells us that the nature of an alpha particle is an helium nuclei, right? And for beta, that's going to be an electron, right? And we know that the charge of an electron is negative, of course, as it relates to the gamma rays. By now, I think we know that that is essentially like light, gamma rays is pretty much electromagnetic waves that is being traveled or being emitted, So, and that doesn't have any charge. So these are some of the things that we must be able to kind of identify. Let me know if you have any questions for me or what you want me to clarify anything. Okay. Yes. So here are some more information as it pertains to alpha, beta, and gamma radiation, right? In terms of the range through which that an alpha particle can go or travel to, that's about 2 to 10 centimeters, right? So if you take out your ruler, you can see how far that alpha particle can travel. One of the reasons is because that alpha particle is so heavy, right? And yeah, so that's the whole reason. And because it's also moving through air, it's going to be ionizing the particles. So you can expect that it's not going to travel very far. Now, as it pertains to what we call here the deflection rather by electric and magnetic field, yes, alpha particle is able to be deflected by an electric and magnetic field at the same time. As in regards to the absorption, right? When it comes on to the absorption of an alpha particle, right? It can pass through paper, but it can also be blocked by paper in a sense, right? But I think this is merely telling us that it can be blocked by paper, right? When you say absorb, it means that it would dissipate in the material, or in other words, we can say it is blocked by paper, right? So a thin sheet of paper can literally stop alpha particles from passing, you know, through the air, but obviously it has to be within the range that is there. As regards to beta particles now, which are pretty much electrons, they can move or travel up to about 1 meter, right? Good. That's basically like the length of a ruler. As it pertains to its ionizing properties, it it's very weak in its ionization property, right? Which just goes to show that because of the fact that electrons are generally much lighter, right? Then you can expect that it's not going to be able to can easily knock off electrons from air particles and all of that. In terms of the deflection, yes, electric and magnetic field can be deflected in an electric and magnetic field. As it pertains to the absorbed by, which is essentially talking about what is it that can stop it, right? Aluminum foil about 3 millimeters thick is able to stop beta particle, providing that it is in the range, right? If it's not in the range, then obviously it will be pointless to use that, because by the time it reaches the 1 meter, it pretty much stops. So anywhere between the 1 meter bracket and you put an aluminum foil in between there, that's supposed to be able to can stop that particle. Cool. As regards to gamma, right? Right. That no, you can't really stop that. You understand? Because I believe it's traveling more like at the speed of light, right? So you can't really stop it. Of course, it is very weak in its ionization property, right? Because of the fact that it doesn't have any mass. As it pertains to the deflection, right, in the magnetic field and the electric field, it is not deflected because it doesn't have any charge, right? This can travel several feet in terms of concrete. Well, I must say several meters. Can pass through several meters of concrete, right? And in a sense, it can also be saying that several meters of concrete can stop it as well. Another thing that we can use to stop it is actually lead, right? So several inches of lead can stop the gamma ray from passing through. What I was supposed to say about the range here was that the range is infinity, meaning that because it's light in a sense, it can travel as far as wherever. So that's how powerful gamma ray is, right? So we can just imagine. Well, let me know if you have any questions. All right, cool. No questions. On the next slide. All right. So we ought to be able to can identify when an alpha decay is occurring, right? And I think most of you would can relate to this kind of thing to some regard. Now, whenever you have alpha decay occurring, as I would have said earlier, that um, you will be essentially giving off a helium element or helium nuclei in the process, and we're saying that the what do you call it again? The proton number, right? The number of protons would be decreasing by two, right? Because you're giving off a helium element or helium nuclei, right? Which is positively charged. So you're giving away two of your protons from the parent element, right? Which is uranium in this case. So whenever you see this scenario taking place, right, then you can easily identify that this is going to be an alpha decay taking place. So the general form is to say that you start out with your parent, which have its mass number and its proton number. If you see that the atomic number has decreased by two, right, then you can easily know that that was an alpha particle that was given off. If you're asked to write out the formula or write out the equation for an alpha decay, then you have to also put that the alpha um, particle is here as one of the products, right? You can't left out that part because at the end of the day, everything should be balanced, and we know it's like a chemistry equation, chemical equation mainly, where you have to balance the number of uh, protons and neutrons on both sides. So at the end of the day, when you add up back everything, you must get um, the total mass number to be in A and the total atomic number to be in Z, right? So this format is very important for us to remember, right? So once you see this just clearly alerts us to say that this is an alpha decay. See? Let me know if you guys are there and understand or follow with what I'm saying here. All right, good, good, good. Right. So yeah, note the general form as I said. All right. So they don't even have to give you the data nuclei, right? They could just say, write out that equation for an alpha decay. You must always remember to say that, all right? If I start out with X being the element and it has, let's just say 300 for argument's sake, and this have 90. I'm just estimating this, right? Then obviously your product is, if it's an alpha decay, then Y, which is your data element or your data nuclei rather, right? This is going to be 300 minus 4 because at the end of the day you're giving off an helium element, so you have to factor that mass of the helium nuclei. And same thing you have to do for the atomic number, right? And you're gonna add this now to the helium um, the helium nuclei, which is, we know helium has a mass of 4 and atomic number of 2, right? So this is what you would essentially get. You see what I mean? Right? This is just an example. Now, Yeah, it seems as though I didn't get to post the one about beta, right? But when it comes on to beta, this is for beta. Cool. So whenever beta, give me a second. Whenever you have a beta decay, right? We said that that is when you're giving off an electron, right? So you have to now factor that in. So your mass number is not going to change, but the only thing that's going to change in this case is going to be your only thing that's going to change is the atomic number. So let's write out that in a sense. Let's just write out what is happening there. Give me a second too. Yeah. So for the beta now, cool. I think such as so this is the general form. This is the general form. The general form says x is equal to y, and then now with this now, right? Your mass number doesn't change, but this is saying z plus 1. Cool. So you're expecting that the mass, not the mass, the atomic number to increase by 1 here because of the fact that the electron is negative. So that's why you add 1 rather than subtracting in this case, right? Because you want the thing to be balanced at the end of the day. So because we know that the electron has 0 mass and has a charge of negative 1, right? If we were to check the stats on this side, z is equal to z, of course. And when we check up the mass on this side in terms of z, we should get back z at the same time. Same thing when it comes on to a, the mass number on this side must be the same mass number on the other side. One typical example for beta is when you have carbon 14. And carbon 14 is a very important one because remember we were talking about the whole thing about carbon dating, right? This is what happens whenever carbon dating is occurring, right? You're taking an isotope of carbon 14, and that is going to obviously disintegrate, but in the process, it's going to form a much larger element because it's going to form nitrogen. So nitrogen is produced in the process of carbon dating, right? This number becomes 7, and we know 7 has to do with nitrogen. Then we plus that to our electron, right? So this right here is important. It's important because it's pretty much that equation that speaks to the product that is formed during carbon dating. Carbon dating, and I've seen it on past papers in a sense, right? So just remember this thing here. Oh my God, what happened now, man?